terminology we're going to be using. It is a little similar to linked list. They're linked together, but obviously tree is a different data structure, and binary search tree is one of the best data structures you're going to be using if you need to keep going back to the data structure and searching for stuff. So I think Amazon uses binary search tree when they're storing personal data onto their network, and it is really fast. And has anybody worked on big O notation yet? So big O means every data structure has a big O. Most of them has a big O of n. That means anytime you try and find something in the list, then it's going to take n amounts to go through it. So give you an example. So let's say you have 1, 2, 3, 4, 5. These are all the elements in an array, linked list, or anything you want. To get to the last one, right? This one, how many is it going to take? It has n equals 2, 5 elements, right? It's going to take you 1, 2, 3, 4, 5 to get all the way to the end. So the linked list has a big O of n. That means it's going to take you n amount. But binary tree has a log base 2 binary search of n. So what's the log base 2n? Can you guys Google what's log base 2n is 100? What number do you guys get? So if n equals to 100 and you do log base 2, what number do you guys get? 6.6 or something, right? So that means if you have 100 elements in binary search tree and you're trying to find the bottom one or the last one, is going to take you 6.6 times to get there. To try to do 1000 elements, log base 2 of 1000, what number do you get? 9.9. So about 10, right? So 9.9, that means if you have 1000 elements, it's going to take you have to look at about 9.9 or about 10 elements to get to the one you're looking for at most. So that's why it is really important, really fast when you're searching for something, to use binary search tree. And binary search tree is really effective because the way you actually design it. So whenever you're trying to add something to binary search tree, that's when you actually decide where do you want to put each element. And then when you go back to look for it, that's why it's really fast. And we'll go through some examples. In this, the graph of log n is something like this, So it never gets too high. It always goes something like this. So this is like 1 million elements, and it'll be something not too big. Every time you have a lot of data that you need to store, and you know you're going to be going back and looking for it, try using binary search tree. All right. So what is a tree? So let's go over tree a little bit. A tree is a nonlinear reference-based searching structure. So right now, this is not a binary search tree. Binary search tree means you have a node, and then you have 2 nodes coming out of it at most, and no less than 2. So you have right now this has 3. This is a different binary. This is a different tree structure. We're going to be working on it later, and not in this class. So if you move forward, you'll see all different types of data structures. Like this one is ternary tree, so it has 3 nodes coming out of it, and this one doesn't have anything coming out of it. That doesn't have any nodes, but that doesn't mean it doesn't exist. We just don't show it. These just shows null pointers for all 3 nodes. So just like this one has one, we can actually see there also has 2 that is set to null. But binary search tree it's exact. It says binary tree. It's the exact same thing. So you have 1 you can actually see. There's also 1 more that you're not able to see. That doesn't mean it doesn't exist. It's there, but it's set to null. So just like all of these, they have nodes. They have nodes coming out of it, but we're not able to. Let's see what else. So terminology between the relationship. So that if you took any of the thing HTML, CSS classes, you have heard about ancestors and parent classes, parent nodes and descendants. The same idea goes here. So this one is the parent node, and all of these are right below that is the child node, and all this is the descendants of the parent node. This is a left descendant, this is a right descendant, and depending on if you have a middle one, you have a middle descendant. So how many descendants does, so if you look at 7, how many descendants does it have? 5. So if you look at 7, you have 1, 2, 3. You're looking at each node. So you that 2, 3, 4, 5. So you gotta go one this way, and you gotta go. I was thinking about the height. My bad. Yeah. So this has 5 descendants. So if you look at 15, how many ancestors does it have? 1, which is just 12. So pretty easy to understand. So how many children does 3 have? Clean this up a little bit. So how many children or child node does 3 has 2? Remember, the child nodes are right below that. These would be like a grandchildren. So this would be like a grandchildren. So this is supposed to be GC. Grandchildren, this is the child node. This is a parent, only looking at this right here. In that scope, this is the parent. About my handwriting. This is the child node, and this is the grandchild node. It's a root. The tree structure typically stores a single node reference called the root. This is the topmost node in the tree. So just like a head node we were working on before with the linked list, tree has a root node. So root node is the first element in the list, or first node in the list, and that is considered a root node. And if you consider this a root node, that cannot be the root node because you have a parent above that. So this has to be the root node. Okay. As long as you have access to the root node, you have access to the whole tree. That's how you can look at it. So just like the linked list, if you have access to the head or the front, whatever you called it, you have access to the whole list. Just like here in the tree, you have access to the root node, you have access to the whole tree. And you can go down the list. Leaf. A node has no children is called leaf and represents a terminal end to a search in the tree. So which one? I already labeled it. The last nodes right here, these are considered a leaf nodes. So it doesn't have anything. Well, it has children, but they're set to null, so we don't actually consider them children, right? So they have pointers coming out of it. They're just set to null, so we don't actually care. So these are the leaf nodes. They don't have any children below that. And you can have a leaf node in the middle, just like F. It's not all the way at the end. So these are nodes coming out, but they're set to null. And when we see both of those two are null, that means there's nothing more to move forward down. Can D be considered a leaf node? It has 1 child, so it cannot be a leaf node. Internal node, a node with at least 1 child is called internal node. So internal, why doesn't D branch left first, but it branches right? Oh, this right here. So this depends on how you defined it. Right now, we're only working on trees. We're gonna get to binary tree in a minute, and you'll see how are we gonna be designing it. So you'll see different types of tree. We're gonna design a tree right now that's gonna have the same elements, and you'll see how it's gonna be designed differently. But right now, this is just a tree, example of a tree. Yeah, so it's not designed perfectly. Yep. So internal node. So internal node has at least 1 child, and it's not the leaf node. So the way I remember the internal node is just it's not the leaf node. If it's not the leaf node, then it's the internal node. This internal node keyword, you're barely gonna use it again, because almost every node except for the leaf node is an internal node. So you can just call it. All right. So the height of the tree. So height of the tree. This is where I got confused earlier. The height of the tree is the longest way down to all the way. That's the height of the. Yes. So if you read coming from the book, I think they refer to a branch node. Internal node and branch node, the same thing. Yes. All right. So the height of the tree is the longest way all the way down to the leaf node. So if you start at 10 right here, what is the height of this tree? Remember, this is like a subtree, right? So this is a subtree of a bigger tree. So what's the height of 10? It is 1, 2. That's the longest way. So that's one of the ways. The other way is just this right here, 1. This is 1, 2, 3. So the 3 is the highest one we have. So or the other way you can look at it, this is 0, 1, 0 level. This is 1 level. This is 2. This is 3. We're working with a subtree, not the whole. We're asking about 10. So that's level 0, 1, 2, and 3. And the height of that would be when you're looking at it. So what's the height of 48? 4. Why is it not 1? So remember, you do all the possible combinations of to get all the way to the bottom. And there's 1. That's 1 right here. This is 1, 2. That's 2. Then 1, 2, 3, 4. You get to 4 right here. And obviously you can do 3, 4 right here, but 4 is the highest one. You always take the highest for the height. So the height is 4. So the terminology and all that stuff. So it is pretty simple. It's not complicated. So figure out the height of each of those nodes. So write down what the height is for each one of them, and then we'll go over that if you got the right answer or not. So the right answers are this right here. So if you look at A height is 0 because we do not have any children under that. So if you look at L right here, that's the height of 1 because at most you can down it just one time. And then if you look at M is right here. The height of that is 3 because 1, 2, 3. Okay, simple enough. Everybody got that? So everything we have done right now, they apply to all the tree structures. So remember, right now in this class, we're going to be focusing on binary search tree, but later we're going to learn about different data structures, different types of trees. So if you see them, the same concept and heights, everything applies to that too. Okay. So binary search tree is, like I said, one of the fastest one. The way you would design it would be, this is the root node, right? Everything on the left of this node has to be less than the x. Everything on the right of this node has to be greater than this, greater than the x. So let's say I have a 10 here. So I don't have x, I have a 10. And I'm trying to add 1. Which side would it go on? So I have a 10, I'm trying to add 1. It'll go on the left side because 1 is less than 10, right? So it'll go on the left side. And let's say I'm trying to add 15. What side would it go on? Right side. So I have 15, I have 10 is less than 15. 15 is on the right side, so we put it on the right side. And you actually do that for each node. So you don't actually do that for, you don't only do this for the root node, you do that for each node you're trying to compare. So going down the list, if you have, let's say, you have a 10 here, then you have 5 here, right? And then you're trying to add 1. You're going to compare 1 to 10, it's going to go on the left. Then you're going to compare 1 to 5, which way is it going to go? Remember, we're trying to add 1. 1 goes to the left here, and then we have a 5 here. This is a 5. Then 1, we're comparing 1 with 5. If we go left, right, right? So we add 1 right there. If there was a 2 here, then we compare 1 with 2, and then we would add 1 here. So we keep going down the list. And remember, anywhere in the binary search tree, you pick up a node. Everything to the left of that has to be less than that element. Everything on the right has to be greater than that element. So the next slide, which one is a binary search tree and which one is not? So start with this one right here. Is this a binary search tree? No. Why is it not a binary search tree? It is not on the left. So this right here, so if you remember, you divide this up right here, everything on the right side of this tree has to be less than 11. It is not. So this is not a binary search tree. How about this one? That one is a binary search tree. Remember, binary search tree only has at most 2 nodes coming out of it. You cannot have more than 2, or you cannot have less than. Well, visually you can have less than 2, but remember there is a null pointer here. So this one is not a binary search tree because we have 3 elements coming out of this. So this one is not a binary. This one right here, yeah, this is actually wrong. This is not a binary search tree. So for the reason being is because 9 is supposed to be on the left side of 11, not on the left side. So this is not a binary search tree. This is wrong. Sorry, I'll go to fix those. But this is not a binary search tree. If you had something like this, this is a binary search tree. Does that make sense? So yeah, something like this is a binary search tree, but the reason being 9 cannot be on the right side of 11. Same thing here. If you have letters, you compare the letters, and comparing letters obviously in your head is a little harder than you comparing numbers. So H, where does R come after H? If it comes after, that's greater, then goes on the right. If C is before H, then obviously it goes on the left side. And A is on the left side because it comes before C. The same concept here. So when we're writing the add function, we're going to have 2 scenarios just like linked list, right? So first scenario was if it's the first element or not. If the root is null, that means we're adding the first, right? And if it's not, this is the rest of the thing we need. What do we need to do? We need to find where it goes. We need to compare the values. So we need to compare, let's say we're trying to add 10, right? Trying to add 10, we start at the root, we compare 10 with 11. Does it go on the left or right? So this is scenario 1, this is scenario 2. That means we already have a 3 somewhere. So we compared the first root data with element that's coming in. That's the element that's coming in. It goes on the left. Then we compare 8 with 10. Does it go on the left or right? It goes on the right. So we create a new node and we add it right there. So when we write an add function, this is what we need to do. Remember, we're going to be creating binary search tree class, and we're going to be writing the add function and all that stuff. So we're going to be doing similar to what we did for linked. Is it possible to add an element that has the same value? No. So in binary search tree, you cannot have no duplicates allowed in binary search tree. So if you're trying to add 11, what we're going to do is we're going to see if this is 11, and then we'll just get out of it. 11 already exists. We're not going to be adding it. Will this be a class or so we're going to be adding a class object. So binary search tree will do it without adding the interface. I know we use interface for the linked list class, but we'll do it without the interface. As the tree is empty, we just start creating a tree, which is just creating a node and assign it to root. And it's like what we just did. We follow the path and keep going down the list until we find the node. The way we were able to add 10 here is because we checked 8 left and right is null. Or remember, depending on left, we're checking left and right because it was 10. We only check the right side. And if it is null, we create a node and add it there. And we're adding 15. We compare it to 11. Move to the right, move to the left, and then compare it again. And this, before adding 15, this was a null node, right? If it is null, we create a node and attach. So you mentioned some companies use BST for data regarding data with names. How does that work? Duplicate names. So that actually, I missed something. In that case, what they do is they used a different type of data. So I have a name, I have an email, right? I have a phone number and all that stuff. So when we're sorting it out, we sort it out by name. Obviously, other people could have my name. Then what they do is they sort it with your email. If you still have, it's not possible to have the same email address, right? So they get sorted by email, and based off of that, they're gonna put you. End of this class, we're gonna do an example, or maybe we'll do that on the Wednesday. We're gonna finish off the compare to method, and you'll see that happening. In so I'd imagine these an ID number or something like an SQL. We learn about yes, exactly. Yep. So you have to take an SQL class. That's exactly what it is. Yes. P value is 15. So yeah, exactly what we just went over. So now if we have this data right here, right? And we're trying to build a binary search tree. This is step 1. We add 33, and that's the root node. Then we're trying to add 48, add 48, right? Then we're trying to add 40, 40 we added, right? And then we keep going, right? So if you look at it, this is how it turns out. We get to -10, or positive 3 looks like this. So this is previous version, and this is the newest version after we add 10. So it is really important to figure out where do you want to add. So which node should be the root node. Remember, if you start at 0 to be your root node, what's going to happen? You have 0 as your root node. What's going to happen to this list right here? Everything's going to be on the one side. Like most of the things will be on the one side because we only have one negative value. That would be on the left side, but everything will be just straight down the list, right? And that is actually not a good way to create a binary search tree. So here's an example right here. So when you're inserting something, so what I just did random on it's the same values. I just did random on it. -10 is the root node. Remember, we're adding it one element at a time. So we're adding 10, and that actually becomes the root node. And everything we add after that will be on the right side, obviously, because it's negative, everything else is positive. And that is not a good data structure right here. It's same thing here. If you have a different type, you have -10 as a root node, and then everything's on the right side. This looks like a linked list, right? Everything's linked together. So that is actually not a good way to create binary search tree. So what you want to do is you want to balance the tree out. So you want to take pick the most middle value. That should be the root node, and everything else should go left or right based off of it. They talk about the balanced tree. So balanced binary search tree is the one that has a log base 2 of n. So in Amazon, what they do is obviously they have so much data, they cannot have a binary search tree, because back in the day when they actually started this, let's say they added something with starts with the A, right? Then after that, every time they add something, there's going to move everybody to the right side. So what they do is they write a function. They write a function to balance the tree out. So they try to find the the mean average of that tree, and they reorganize the tree to make it balanced. So they find whatever needs to be in the middle, they make that the root, and they reshuffle everything. So when they're searching for it, it's faster. And they do that. They usually do that during non-busy time, right? So they may do that. I don't know when Amazon does it. I'm just telling you, if you need to work with the data, you want to do it when it's not busy, and you're reorganizing everything that take a lot of power, computing powers, and you don't want to slow everything else down. So you want to do it overnight or something, or during an off time. So remember, only the balanced search tree has a log base of 2, log base 2n. This is the reason is balanced tree is because the height on the left side is the same as on the right. So this is balanced and this is not balanced because the right side is weighted heavy. So if you wanted to balance this tree out, you would find the medium or the mean average. In this case, I think we talk about it next slide. The next slide, it would be F, and everything you add after that will be just on the left or the right. Pick the middle element, is either F or E. Tree implementation, let's go and do that. So we're going to create our own tree. We're going to create our node class. We can go and create just like what we did for link. So it is 10:51. Let's take a break, and when we come back, we're actually going to. All right. So here I created a new project. I just call it trees. You can actually call it whatever you want. So here what we're going to be doing is we're going to be creating the classes we need to add the binary search tree. So I'm going to right click on this. I'm going to add a new class. I'm going to call this binary search. I'm going to call it int. The class we're going to design is only going to work with integers. I'm going to call this binary search int tree. And inside this class, we need a node class. All right. And then we need the data structure to build like add method or something like this for binary search tree. So first thing I'm going to add is the private class node. So if you're not familiar with inner classes, this is what this is. Inner class. Hopefully at this point everybody knows what an inner class is. So inner class is a node. Remember, each one has 2 nodes below that, and every node is either a null or has a data to it. That's how you actually build the tree itself, right? So each one of this is a node, and that's what we're going to try. What goes inside the node? What are the fields for the node? So fields or attributes, data. We need the data, so we need private int data. Remember, it's going to be integer, so that's why I have integer data. If you want it to be a string, binary search tree, you put string here. We need left and a right. So we need, remember, in this case, we won't have next node. We'll just have left or the right node. So we'll just do private node itself is going to be left, and private node is going to be the right node. And then I'm going to right click inside the inner class, and I'm going to generate the constructors. So the first constructor I'm going to add is just the data. And in that, what we're going to do is we're going to set the left and the right node to null, and we're just going to create a new node. So we have the constructor in this one where this dot left. Even if you don't do that, it is set to null. So I'm just going to do it just in case. This dot right equals to null. So we're creating a new node, and we're setting the left and the right to null. Another one, I'm not sure if you're going to need this right now or later. I'm going to add another constructor that takes all 3 of them. And we define what the left node is going to be, what the right node is going to be, and we just add it just like this. All right. So that's the inner class. That's the node class. Now we'll come back out to our binary search int tree class. This is what the data structure is. And what do we need in here? A root node. So before we linked list, we were doing a head node or a front node. In here, we call it a root node. Same, call it private, and we're going to be node and root node. Same concept. And we can actually add the size. So we can add integer of size, and size would keep track of how many nodes are in the, so it's not going to keep track of height or anything like that, just as that. Later on, we'll go and add the height and all that stuff in there, but for right now, let's keep it simple. Just add root node and the size. So here, what we're going to do is we're going to add a method. We're going to add a public. It could be Boolean or it could be nothing. We'll add the Boolean, and this is going to be the add method. So we're going to write the add method, and returns when we're able to add something, we return true. If we're not able to add something, we return false. That means if 5 is the element that's coming in and the 5 already exists, that means it's going to return false because we were not able to add 5 because it already exists. Something like that, right? All right, going back to the slide, it showed you the slide there. When we were trying to add something to the root of the tree or to the binary search tree, we divide that up into two parts, right? What were those two parts? Check if the root has check if it has a root, or if the root is null, right? So what if the tree is, first one would be, what if the tree is empty? How do we check that? We check root equals null. If it is empty, what should we do? Create it. If not, create it. So we set root equals 2. We set it to new node and pass in the element. So the element, the value they're trying to add, if root is null, that means it's an empty tree. We create a new node, and we're using this constructor to create a new node. That means left and right is going to be set to null, right? And every time we add something to the create a node or add something to the tree, we're going to increase the size. So I'm going to do size plus plus. All right. So now what we need to do is we need to go down to the second option would be the else part, right? We should make private in size equals to 0. You mean this right here? In Java, the primitive data types like integer or double, if you don't set anything, if you don't do anything like that, it's automatically 0. Yeah. So yeah, you can do something like this, or even if you don't do this in Java, it's automatically set to 0. So that usually only happens with a primitive data type. And with an object like this one is the default is null, but this one is 0. Yep. So I know it looks like it's not initialized, but Java is really nice and initializes this to 0 automatically. All right. So the next one is, what if tree already exists? So that's the other thing. And at this point, the else part, we don't know how big the tree is. If it's one node in there or it has 100 nodes in there, we don't know when we get to this part. So now we need to go through the whole tree. So let's say we have this tree. So we have 6, really bad at drawing. And then we have 5, and then we have 10, then we have 4, then we have 3, and then we have 15, we have 7, something like this. Is this a binary search tree? What do you guys think? Is this a binary search tree? So it doesn't matter where you divide this tree into, everything of the left of that node is less than, everything on the right is greater than. So it is a binary search tree. So if you do divide it up at the root node, which is 6, this is 6. And 7, 10, 15 is greater, 5, 4, 3 is less than. Okay. So let's say the data structure looks like this, and you're trying to add 8, right? So 8 comes in here, we compare it to this, then we go down here, and the 8 should be added right there. But how do we actually go down the list? We cannot use any kind of loop to go down, right? So the best way to do that would be, because they don't have indexes or anything like that. What we're going to be using is we're going to use recursion to go down to all the way to the bottom, and we're going to use recursion right here. So we're going to call a method that is going to be a recursive method. So what we're going to do is, this is a public method that everybody else is going to see. I'm going to write another private Boolean add method that's only visible within this class, and that method will take the current node, test to see if element is less. Yeah, so we'll go and add that in there. Yeah, so when you're writing in recursion, you just gotta make sure it's not an infinite one. It has to be finite, and we need. How do we know if it's a finite recursion? How do we actually stop the recursion? Base case, exactly. So if you're not familiar with recursion, I think we covered last quarter and the quarter before that too. If you took it with me, 219. Recursion, you need a base case to stop the recursion, right? And that base case is what stops the recursion. If you don't have that in there, then you'll get into the Stack Overflow or infinite recursion. Okay. All right, so that node, that method is actually going to take the node that you're at right now, so like a current node, a pointer to that. Remember, if you cannot change the root node pointer, you got to make a copy of that. If you just pass it in like this, that would make a copy of the root pointer. And the next thing you need is the element that you're trying to add. And inside of this method right here, what we're going to do is we're going to return we're going to call that function, and we're going to return whatever that function is returning. And we're going to pass in these things. So the root, we're going to start at the root. Remember, the only way we get into the else part is because root is not null. That means we pass in the pointer to the root, and it's going to make a copy of that. And we're going to call that current. And then we pass in the element as it is. Comes in right here. And this returns a Boolean. We return this as it is. If we were able to add it, we return that true. If we were not able to add it, we return false. All right, so now we come in here. We need to write some cases, right? So we need to write the base case. What happens and how do we actually stop the recursion? What could be the base case? Either the root is null or the current. Yeah, that could be one of the base case, or the other base case could be the element equals. If the data is already in there, then we stop it, right? So we do element equals to current dot data. That is the case. What do we return? Or what should happen inside this base? So this is the element already exists, we return false. Then else if, what should we do in the else if? So remember, we need to compare the data. Depending on the direction of that data, we move left or right. And how are we comparing the data? Left or right, I mean less than or greater than. So it's going to be element is less than current dot data, just like this. And then we need else if. What should happen here? All right, hello, hello everybody. Sorry, the previous video, the recording was cut off, and I kept recording, and at the end I found out it wasn't recorded. So here is the missing part. So we're trying to add add method to our binary int search tree. So the add method, we have one method that is public that the user is going to be using, and this is the helper method that we are adding, which is private, and it's only visible within this class. So we have the base case. What if the data that we're trying to add already exists? We return false. That's great. Now we need to do the recursive call. So recursive call is when you need to figure out you need to go left or right. This is going left. This is for left, and this is going right. Right. So let's draw the. I'm going to draw the example and show you how that's going to look like. So let's say you have root is a 10, and then you have 5 here, and then you have 15 here, right? So that's what the excuse me tree looks like. So this tree, this is the root, and the element we're trying to add is 6. E equals element equals 6. That's the element that's coming in here. And how are we going to determine where does it go? So now we have the base case. If 6 equals 10, that is not the case. We go into the else if. We're going to compare 6 is current.data. Remember, current is pointing, root is pointing here, and we just made a copy of root. Current, this right here is pointing here. That root is coming from when we actually originally called the function, right? All right. So make a copy of the current, and then we're checking current.data. Current.data is 10. We're going to compare. 6 is less than 10. It is. In this case, we need to go left. And what happens when we go left? We need to check if the left is null or not. So if it is null, that means we add 6 right there. But if it is not null, we keep moving down, right? So we can say if current dot left does not equals to null. So if it does not equal to null, then we need to do recursion and keep moving down. And the recursion, what we do is we pass in that node. We pass, so if it is not null, in this case it is not null, we pass in current dot left and make this the current. So we move the pointer point here when we call recursion again. So in that case, what we're going to do is we're going to do add function current dot left, then element stays the same, just like this. And then we call recursion, we call the same function again, and now current is pointing over here, right? And then if the current is pointing here, what should happen? Remember, this has a left and a right, which is null. This is a null right here. And then if it is not this is not null, right? So if it is, in this case, it is null, left and right is null. We need to check, excuse me, we need to create a node. So we need to do current dot left equals to new node, and we create a new node using the element. Every time we add a new node, excuse me, we increment the size, and then we return true. Just like that. So this is actually a little bad example. Let me change this out. So let's say the element we're trying to add is 4. So if you have 4, we start here, check if this is left, move left or right, we move left. And then in here, we check current dot left is null. In this case, we get into this part. It is null. We create a new node. We add that element in, number 4. We increment the size and then return true. And when we use this constructor right here, that is this constructor right here, and this uses left dot null, right dot null. So these have left and right pointers, but they're set to null. Okay, everything else in the picture stays the same. Right. So now we have. I'm gonna clear the screen up. I have a lot of things going on. All right. So now this is a recursive call. So, and this would be known as the base case. So base case would be just stopping the recursion. It stops the recursion, it adds the new node, and that is it. And now we did this for the left side, we do the exact same thing for the right side. So if you want to, we can copy this. I'm going to copy this, add it here, and instead of left, we're going to check all the rights. And we're going to add it to the right. Remember, this case is for the right. So now if you look at the whole picture, big picture, we have 3 cases, right? So we have if, else if, and else if. So there are 3 cases when it's the data equals to the data, element equals to the data. If it's less than, if it's not those 2, then it's got to be this one, right? So we don't actually need this if statement. We can take that out. There's only it's only going to be 3 parts: equals, less than, or greater than. So if you don't have an if statement here, just the else part, that should still be okay. Okay. So right now it's complaining that I'm missing a return statement here. Remember, this function is returning a Boolean and it's complaining that it's not returning a Boolean. Even though we have a lot of return true, return false, return statements, the reason it's saying that is what happens if it gets into this case, if statement, what happens if it gets to this case right here? There's no return statements here. But if you remember recursion, if you have a return type here, you need to return that same value and move it up the chain. And whenever you call recursion, you need to return that value as well. So when you call recursion, doesn't matter if it's true or false, that it's going to be coming from the base case, right? And it's deep down on the layers, and you need to carry that up onto the wherever it was called from. So the way you can do that is just return whatever that function is returning. And now that call is disappeared, and this is what the function should look like. Okay. So this I think I got everything. Yeah, so if you have any questions or concerns, let me know. And that should be it. So this video will be divided into 3 parts.